Okay, welcome back. So in this video we're going to look at examples of invertibility and stability. I've got the definitions here again. A system is invertible if distinct, sometimes you'll see distinct instead of unique. Distinct inputs produce, oops, I got a typo there, distinct, not distinct, outputs. Stability, a system is stable if bounded inputs produce bounded outputs. So to introduce these concepts, I showed you systems, examples of systems that were not invertible and not stable. And in these examples, in the present video, I want to demonstrate to you how you would show that these properties hold for all valid inputs, because that's the way you prove things, is to show that it's true always. Whereas if you disprove something, you only have to find one counterexample. Okay, so in the first example, I want to consider, is the accumulator invertible? The accumulator, the input-output relationship of the accumulator is this one, which we've seen many times now, that the value of the output right now is the sum of all of the values up until and including right now of the input. So we write that like this. Now you can imagine, you might guess that this is invertible. If I told you that, remember the concept of invertibility is trying to be able to get what the input was by observing the output. So if I told you the output at the last time step, maybe at -1, if the output at the previous time step was 2, and now the output is 4, and the system is an accumulator, could you tell me what the input right now was? Well, this thing's an accumulator, so if y of -1 is the sum of all of the inputs up until and including -1 is equal to 2, and then a new sample comes in and now the output is 4, then the input at that time must have been 2, because 2 plus the 2 gives us the 4. And if the next input is, let's say, 3, then you know then that the input at that time was -1, because when we take -1, we add it to the previous accumulation, we get that the updated accumulation is 3. So by just stopping and thinking for a second, before we get into proofs and yada, 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 by stopping and thinking, we have a good guess that this should be invertible. We should be able to get the input given the output. Okay, so let's see if we can do that. So we're going to use the same strategy that we were doing just now, where we considered previous inputs and outputs. So y of n-1 is k goes from -infinity to n-1 of x of k. Okay, and if we expand y of n, you'll notice this is x of n plus, or I guess let me reverse this. So we've got an infinite sum here, plus all this stuff, plus then maybe the x of -2 term, and then the x of -1 term, and all those things, and then the x of n term, right? Okay, I can collect all of these things. That is, k goes from -infinity to n-1, all of the previous ones. And then I've got added to that then the current one, like this. Okay, so again, this is y of n. Okay, well, I identify this thing. This thing is precisely this thing here, right? This is y of n minus 1. And so can we get the input back by observing the output? Yes. The input at any time is the output at that time minus all, minus the output at the previous time. So we conclude the system is invertible. The accumulator is invertible, yes. And because we just showed that we can get the input back given the output. By the way, if you're thinking in terms of calculus, the integral and derivative operations do not apply to discrete time. The accumulator is the analogous operation to integration. Integration is a sum or a sum of areas, right? And accumulation is a sum as well. And then the first difference, this is what we have here, right? First difference of y. So the first difference is like the differentiation operator in continuous time. The differentiation operator is a limiting difference. You should have learned that in calculus. And so here what we're saying is that the inverse of accumulator is the first difference. That's an important relationship. Just like in calculus, the inverse of the integration operator is the first derivative. All right, so we're going to move on now. We're going to look at stability, an example of proving stability. Okay, so let's say that we had a system whose input-output relationship was like this. The output was 1/2 to the x power. And we want to know, is this stable? Is this system stable? Okay, now we want to start with a good guess. Just kind of think, what do we expect the answer to be, yes or no? And then we have to show it. So if I have, remember the concept here is that if the input is bounded, that is, if the input does not go to infinity or negative infinity, the output needs to stay finite as well. So if x is finite, is 1/2 to the x going to be finite, is the question. And it is. It is. If x is 10, well, 1/2 to the 10th is still a finite number. If x is 1,000,000, 1/2 to the 1,000,000 is a finite number. But remember, we can find a b, and so that x is never greater than that b. Well then, y will never be greater than 1/2 to the b power. So we suspect that this system is stable. So now we have to prove it, and we just gave the argument in English, but now we were going to prove it mathematically. So you have to show this for every input, every bounded input, that is. Oh my gosh, how do I do that for every bounded input? I cannot possibly choose every bounded input. Well, you don't make any assumptions other than the fact that it's bounded. So suppose x is bounded. That's the only assumption we're going to make. Okay, so what does that mean? Well, that means that the absolute value of x is less than b for all n. Well, that means that x can be squished between plus and minus b. Do you remember that plot from the one video before? Right? So you should be comfortable with that, and feel free to pause the video if you need to. Okay, So now with this, and I'm trying to make it look like my system input-output relationship. So if I raise all of these things to a base of 1/2, then I have something like this. 1/2 to the minus b is less than 1/2 to the xn, and that's less than 1/2 to the b. Okay, and now I look at my input-output relationship and I identify the middle term here as y of n. So now I can write down 1/2 to the minus b is less than y of n, and that's less than 1/2 to the b. All right, and I'm almost done then. Notice now what we have is this is a constant, right? That's just a constant. And this is just a constant, right? Because the idea again was that because the input is bounded, then I can find a constant b, a finite constant. So that's a finite constant. Then this is also a finite constant, and this is also a finite constant. And therefore, y is bounded. Y is between these two finite constants. Y is bounded. Right? Y does not go to infinity because y is less than this constant. Y does not go to minus infinity because y is greater than this constant. So look at my proof here. I started with the hypothesis that x is bounded, and I made no other assumptions about x. Not that it's the sine wave or that it's a constant or whatever. I made no other assumptions, and I was able to show that y is bounded. Therefore, for any bounded xn, I get a bounded yn, and the system is stable. That is how you show stability. But it requires that or it doesn't require, but you should have a good idea or a good intuition of what it is that you're going to do at the beginning. Okay, do I suspect that this is stable? If I suspect it's stable, then I know that I have to show it's true, prove it's true. And if I suspect that it's not stable, then I just have to find one counterexample to show that it's not stable.